Okay, so it's my pleasure to introduce next speaker, Professor Vishvesh Kumar from the Department of Mathematics at Ghent University. Vishvesh is member of the Analysis and PD group here in Ghent. He's my friend and colleague. Vishvesh got his PhD degree in Indian Institute of Delhi. He has more than 40 publications in analysis and hypergroups. So I am very happy to have you today here in our event here in Colombia. So Vishvesh, you have 40 minutes plus 5 minutes questions. So
okay, can I start now?
Yes, you can start.
Okay. Thank you, Duan. So before starting our main talk, so I would like to say a few words. So first of all, I would like to thank the organizer for giving me this opportunity to speak here. And secondly, I'm speaking in English and all the talk are in Spanish. In fact, the official language of the conference is Spanish. So I apologize for that. I have to learn. But in fact, you can ask me any question in Spanish and Duan will help me to translate it. And last, this talk will be based on my joint work with Duan and Mariana, Michael Rujansky from Ghent University and Nia Tukumagamteo. So as my title says, I will talk about LP-LQ boundedness of pseudo-differential operators. So Duan already yesterday set up a platform and he discussed like good motivation why we study pseudo-differential operator. In fact, he defined it, everything, but I will just recall the definition quickly, then we will move on. So a pseudo-differential operator on Rn with symbol sigma A is an operator which is of this form. So if you remove this, so it's an integral over Rn and you insert the symbol sigma A inside. If you remove this sigma A, then it's just nothing but it's f of A because it becomes the Fourier inversion formula on Rn. So it's like you are, so if you remove this, this will be f is equal to f inverse Fourier transform of f. So when you insert the symbol, it's like breaking the symmetry of the Fourier transform. So some people also refer it to pseudo-differential operator as breaking the symmetry. So when the symbol sigma A is independent of first variable, only depend upon psi, then we call it Fourier multiplier. In fact, every Fourier multiplier can be characterized as this identity. So why it called Fourier multiplier? Because when you apply Fourier transform on the image of a function, it gives a multiplication by a complex number, and that's the multiplier. So sometimes we also call a symbol of a Fourier multiplier a multiplier also, or Fourier multiplier in fact. Okay. So now in this talk we will also discuss about some spectral multiplier theorem. So let us recall the definition. What is the definition? So we consider a positive self-adjoint operator on L2X, so X is a measure space. You can take sigma finite measure space such that the spectrum is contained inside the positive real line. Then for any bounded Borel function using the functional calculus or spectral theorem, you get the spectral decomposition of a spectral resolution of this L, operator L, and then you define phi of L as integral over 0 to infinity phi of lambda d e lambda, where e lambda are the spectral measures. So now the main problem in harmonic analysis is to study boundedness of Fourier multiplier or and pseudo-differential operator, because it has a very vast application in PD once you study the boundedness and these properties. So there are many so when we study boundedness of a pseudo-differential operator, so what we want to find? We want to find the condition on the symbol such that this operator is bounded from one space to another space. Or when we study boundedness of a spectral multiplier, we want to find the condition on function p. So there are many conditions. One of a classical condition is Hormenden-Millin condition. So it says if the symbol is measurable function, and for every psi here on smooth function, if symbol satisfy this condition, which is for every s greater or equal to n by 2, where n is the dimension of Rn, then the Fourier multiplier operator has a boundary extension from LP to LP. So this gives a condition on symbol such that the operator A Fourier multiplier is bounded operator from LP to LP. This theorem has a long history and extended to many different settings by very eminent mathematicians around the world, and some of them I would like to mention here. So it started with Hormender. Hormender was the, and then Clark and Stein, Taylor, Kaufman and Weiss, Pfefferman, and then for non-Euclidean spaces, Seeger, Anker, and then calling Sikora. They study for compact symmetry, non-compact symmetric spaces. Then for Lie groups, it was studied by many people, including Alexopoulos, Muller, Ricci, and then Thangavelu and Baxi. They study similar Hormender-Miller condition for pseudo multiplier, which is kind of a particular case of the pseudo-differential operator, which we will study in this talk. And then Ruzhansky and Wirth, they study for compact Lie group, then Fischer Ruzhansky for Getty Lie groups, then recently Duan and Ruzhansky, they study for pseudo multiplier. They prove similar estimate for using this Hormender-Miller condition for pseudo multiplier of Hermite operators. So now in this talk, we mainly focus on LP-LQ boundedness. So in 1960, Hormender, in his seminal paper in Ectamath, Hormender established this theorem, which says if the symbol of the Fourier multiplier satisfies this condition with this range of P and Q, where P is less or equal to 2 greater than 1 and Q is greater or equal to 2 less than infinity, then A has a bounded extension from LP to LQ. So this is very classical theorem. Later, Ljorkin extended this, or not extended, improved little bit the range of this, because here you see that P and Q are separated by 2. But here, then Ljorkin proved this, but for R is equal, for N is equal to 1, that if you take P and Q, this condition P less or equal to Q is must condition. It's when you study LP-LQ boundedness, then if your symbol satisfies this condition, then A has a bounded extension from LPR to LQR. So it's only one-dimensional case. So recently, this theorem was, especially we'll talk about the first one. So this condition or theorem of Hormender was extended to many different settings by Ruzhansky and his collaborator. So we'll explain it here. So for non-Euclidean spaces, so in particular for compact homogeneous spaces and for compact Lie groups, Akiljanov, Nur Sultanov and Ruzhansky extended it, and then after that they extended it with Majid. They extended it for compact quantum group, which was yesterday quantum groups was introduced. So, and then they finally introduced this year for like recently published in Journal of Functional Analysis for locally compact unimodular groups. And then I study with Ruzhansky for compact hypergroups or commutative hypergroup. Then finally we study with Duan and Tukmagamtev for smooth manifold using the non-harmonic Fourier analysis. So non-harmonic Fourier analysis on manifold, initially it was developed only for open subsets of Rn by Ruzhansky and Tukmagamtev, and later it was extended to manifold with Julio Delgado, which is here, and it is nice to have him. So now this extension is not only extension of a particular theorem. Actually, this extension gives a very special method for spectral multiplier theorem, because spectral multiplier theorem was very special in harmonic analysis. So they provide a very strong theorem to prove result of a spectral multiplier theorem. So here we will see at least one example if time permit. So what are the ingredients to prove this Hormender multiplier theorem? So first one is the Pele inequality. So classical version of Pele inequality goes back to little Pele, is very classical. Then Hormender is stated in his paper, and the credit he has given to little Pele itself, but he proved for Rn. So it says, like, if the measure of this set for every t is dominated by C by t, then this inequality hold, and this is called a Pele inequality. Pele inequality is very powerful to obtain, in particular, Hardy-Littlewood inequality for compact Lie groups and for quantum Lie groups quantum groups and for other groups. And it was the purpose of Ruzhansky and Akeljanov in the first paper to study this kind of inequality and then prove LP-LQ multiplier theorem. And the second inequality which is used in to prove these estimates is Hausdorff-Young-Paley inequality, which says if you take P between 1 and 2, and for any B between P and P prime, which is Lebesgue conjugate of P, and if your function phi, positive function P satisfy again this condition, then you got Hausdorff-Young-Paley inequality. So why is Hausdorff-Young-Paley inequality? Because it is obtained using the Hausdorff-Young inequality and Paley inequality. So Hausdorff-Young inequality says that your Fourier transform is bounded from LP to LP prime. So if you put here B is equal to P prime, then this term will go away and this will be P prime, so you will get P prime norm of the Fourier transform. So this becomes just a Hausdorff-Young inequality. And when you put B is equal to P, then this is nothing but Paley inequality. So this inequality is obtained using interpolation. Now we want to prove this LP-LQ boundedness for non-harmonic on manifolds using the non-harmonic analysis. So let us see what is the non-harmonic analysis. So for non-harmonic analysis, we fix a pseudo-differential operator of order M inside on the interior of a manifold if manifold has a boundary. On a smooth manifold, in fact, Duan defined this, how to define pseudo-differential operators on a manifold yesterday. And we fix some boundary condition if it has boundary, if it doesn't have, then it's fine. So if we fix a boundary condition such that L has a discrete spectrum such that the family of eigenfunction form a ridge basis for L to M. So this is our basic assumption or data. Now here we note that L need not to be self-adjoint or elliptic operator. So what are the example of such? So the basic motivation to introduce this analysis was to extend the pseudo-differential calculus developed by Ruzhansky and Turunen to more general settings. So on the torus which they developed, it was the motivation to develop for different settings, which are because pseudo-differential calculus on torus is associated with the Laplacian on the torus. So here, if you have any operator which may not be self-adjoint and with some boundary value conditions, then how to develop this? So this was the motivation to develop it, but later it was extended to closed manifold with boundary. Manifold with boundary, and in fact this can be extended to manifold also. So some example in this setting, of course, Laplacian on any closed manifold, or you can consider Hermite operator or harmonic oscillator in this setting. And okay, so let's be precise. So we do not the set of discrete set of eigenvalue by in letter I, and the spectrum will be denoted by every eigenvalue will be denoted by lambda xi, and this is the like u psi are the eigenfunction. That means L of u psi lambda psi u psi on M, and the eigenfunction satisfy the boundary condition. Boundary condition are here arbitrary. It's not like very precise, but it is some boundary conditions so that these conditions hold. Now L is not self-adjoint, so we should have conjugate spectral problem also. So suppose the conjugate spectral problem is this, the corresponding eigenvalue is lambda psi with eigenfunction u psi, and it satisfies the boundary condition BC star. Now moreover, we also assume that the eigenfunction u psi and v psi are normalized. That means L2 norm is 1, and moreover we can take even this u psi system of u psi and v psi, both the system are bi-orthogonal. That means a system is bi-orthogonal if this condition hold, like u psi is v psi inner product of u psi and v psi, L2 inner product, which is Hilbert space inner product is 0 if the indexes are different, and indexes then it's just 1. Now it is a classical work of Gelfand and Bari that if you, because we assume that u psi is a basis, ridge basis for L2M. So if u psi is a basis, then automatically if you have a bi-orthogonal system, then V psi is again a basis of L to M. Now, to introduce Fourier analysis, we need some spaces, because here this boundary value, these are boundary value problems, so we have to take care of these boundary conditions. So for that, we need to introduce some spaces. So first we define the smooth functions. Smooth functions are defined intersection of all domain of possible natural power of model operator L, which are fixed in the beginning, and the domain of Lk is defined like this recursively. Now in this way, the boundary condition automatically satisfied by every power, and we give a Fréchet topology on this space smooth function, and so so this become a Fréchet space. Similarly, using the adjoint operator L star, we can define a smooth function corresponding to L star. Now, using the ridge basis condition, it can be seen that these spaces are dense in L to M. Now, to define Fourier transform, we should also have like a similar to Schwarz function on Rn, like we have in Fourier transform. So on the opposite side, we have here indexing set I, which is discrete. So we should also have here similar set. So we define S of I, which is kind of Schwarz function, consists of all rapidly decreasing function. That means for every n, there exists a constant which depends upon the function also on this natural number n, such that this condition hold, which is the Japanese bracket is given by here 1 plus norm of eigenvalue corresponding to J square plus 1 upon 2m. M is the order of the operator L. So this also play a role here. Like so every time you change the operator, everything change. So we give a Fréchet topology here using this norm, and this become a Fréchet space. So having these two space, now we define our Fourier transform. So the Fourier transform is a bijective homomorphism defining given by f hat, which will know by f hat, also sometimes by script L, also that integral over m fx, and this we put here eigenfunction of L star. So if you thought about torus in Laplacian, you have exponential, or Rn you have exponential. So those are the, in Rn we cannot take Laplacian on a spectrum of Laplacian on Rn is not discrete. But on torus we can take Laplacian, and that's exponential, but Laplacian is self-adjoint, so we don't care about which eigenfunction are there. But here we have to take care of. So this is the eigenfunction of L star, and similarly, and then the inverse Fourier transform of L is given by this formula. So when you put here Fourier transform, this gives the inversion formula. So here in inversion formula, the eigenfunction of L appears. And similarly, we have Fourier transform with respect to L star, which is actually given by this formula, where so instead of now eigenfunction of L star, we put here eigenfunction of L. And as you can guess, in the inversion formula, we will have eigenfunction of L star here. So now, as I explained, to define the pseudo-differential operator, if you have a Fourier inversion formula, you just insert the symbol to define a formally a pseudo-differential operator. So similarly, we will have here also, because we have Fourier inversion formula. So we will do now. When we have Fourier transform, the first identity or first question is asked, like, what is the do we have Planck identity? So for that we need L2 spaces or Lebesgue spaces on the index set I, because our Fourier transform is from smooth functions to S of I. So here, so how we define L2 spaces? L2 spaces are defined as the linear spaces of complex valued function on I, such that the inverse Fourier transform is inside the L2 of M. Then we endowed this space with this inner product, then this become a Hilbert space. Now having this L2 spaces, and this definition looks little, because when you consider suppose I is equal to Z, then you may thought like U psi, and we have here B psi, but why this appear Fourier transform? It is because only to have Planck identity in this setting. Okay, so with this definition of L2 spaces, we have the Parseval identity, and in fact, the Fourier transform, Planck identity given by this. So Planck identity says that Fourier transform is a isometric isomorphism from L2 to L2, small l, capital L2 to small L2 here. Now, after Planck identity, to prove our main objective like Pell inequality, Hausdorff-Young Pell inequality, we need Hausdorff-Young inequality also, and for that we need LP spaces on index set I. So how to define LP spaces? So LP spaces are the linear functional on S of I such that this condition hold is a weighted LP spaces. You can thought of as a weighted LP spaces on Zn. So for P between 1 and 2, we put here eigenfunction of L, but for P greater or equal to 2, we define LP spaces suitably because we need to care if it's L is self-adjoint, these conditions match, so it doesn't matter where you could use I or V psi, but when not self-adjoint, we have to care about the self-adjointness to prove our main result or to develop analysis. So, and for infinity, for P is equal to infinity, we define essential norm. So here also is V psi is equal to, we put weight as a infinity norm of the eigenfunction of L star. Now we already defined this LP space for L is equal to 2 here. So if you, but it's not a kind of a problem because for P is equal to 2, this definition matches with the earlier definition. So it's not a problem. With this having these LP spaces, now this is the Hausdorff-Young inequality we have. So it says if you have, our P is between 1 and 2, and P prime is a Lebesgue conjugate of P, then that exists a constant Cp such that LP prime norm of Fourier transform is less or equal to constant times the LP norm. So here Cp is exactly, we don't know, 1 in the case where L is non-self-adjoint, but if it is self-adjoint, it's exactly 1 in this case. And similarly, Hausdorff-Young inequality for L star we also have. Okay. So now we have Hausdorff-Young inequality, and so how to define pseudo-differential operator in this setting? So for a smooth function, which means that when a smooth function as a x, L pseudo-differential operator, because it depends upon the model operator L, we define pseudo-differential operator like you insert the symbol inside the inversion formula of the Fourier transform, and this is the pseudo-differential operators for this harmonic analysis. And if symbol M is only depend upon psi, then we call L Fourier multiplier, which is again, you apply Fourier transform, you get this multiplier factor and Fourier transform F. So it's similar to Rn or Tn or torus. Now we also study a different kind of pseudo-differential operator. It's not different, it's a kind of a hybrid case, you can say. It's called pseudo-multiplier, which was a study by Duan and Rudhansky earlier, and before that Thangavelu and Bakshi they study. So a pseudo-differential operator is called pseudo-multiplier if there exists a continuous function from manifold cross R. So here we don't have I discrete set, we have a continuous set here to see such that this condition hold. So if this depend upon the existence of this function, so there are infinity many choices, so this depend upon the existence of function. In fact, we can prove that the pseudo multiplier and pseudo differential operator has 1-1 correspondence. Now we have this condition, then in fact we can see that if we can define we define a densely defined operator given by this, then we can clearly see that this is nothing but pseudo-differential operator related with this symbol. Okay, so it's a particular case of the more general pseudo-differential operators, or you can say like is without x it is just a spectral multiplier. So it's spectral multiplier, you can also call it. So now our main is first aim is to prove LP boundedness of the pseudo multiplier. So that means we want to find condition on this symbol M. So for that we need some condition, because we are working in more general condition, more general setups. So here we need some condition to prove this. So first condition, so there are three conditions. So first condition, we assume here, the first assumption for that is the eigenfunction have polynomially grow polynomially. So for Hermit for Hermit operator, if you take Hermit operator or harmonic oscillator, these conditions are in fact very sharp, bound known. So this work. So here we need to assume this. Secondly, we need to assume that operator, positive operator L0 L is satisfy kind of wild eigenvalue counting formula. This kind of, so when M is our closed manifold and L is a Laplacian, then you can replace this number Q you can replace as by dimension of the manifold. And thirdly, we need to assume that the spectrum of this operator lies from L1 to infinity to avoid the zero actually. And with this, having this condition, all with these three conditions, we have our which is, so if you have a smooth manifold with boundary and possibly without boundary also, then the pseudo multiplier defined by earlier we define. Then if the symbol, as I say, that we find, we need to import the condition symbol on condition on the symbol M. So if the symbol satisfies this Hormender-Milling type of condition for S greater than, for Rn we have only n by 2, but here is modular where Qm is any number which we get in the proof, and Q is the this appear in wild eigenvalue counting formula. Then the operator A is bounded from LP to LP. So this is our first main result about boundedness, LP boundedness of the pseudo multiplier. Now we'll discuss LP LQ boundedness. So this is a corollary of this theorem where we get a Marcinkiewicz type condition for the boundedness of pseudo multiplier. So these kind of conditions are called Marcinkiewicz conditions, which are introduced by Marcinkiewicz and later studied by many people. So it's a kind of corollary of that, our first result. So for the study LP-LQ boundedness, so we need to extend Paley inequality. We need to prove Paley inequality and Hausdorff-Young Paley inequality in this setting. So the Paley inequality is given by, so what is the analog of Paley inequality in this setting? So here we have, there we have Rn and Rn in both sides. Here we have one side manifold and then we have discrete set I. Okay, so for every P between 1 and 2, if this condition satisfy, then if you consider a positive sequence in I, because I is discrete now, so it's a function is just sequence, and then if this condition satisfy, which can be written in discrete set, that condition which I earlier showed for Paley inequality on Rn is equivalent to this condition, then we have this inequality. So here this condition is required on the eigenfunction like supremo, or the quotient of eigenfunctions are finite because it is needed in this case. And when L is self-adjoint, then this will be just trivial, because these two are 1, so it become, these are the same. U psi is equal to V psi, so it's become just 1. So for self-adjoint case, we don't require. To work in more generality, we require these conditions. Now second one is our Hausdorff-Young Paley inequality. So we have Hausdorff-Young inequality and Paley inequality now. So we, by interpolation, real interpolation, we get Hausdorff-Young Paley inequality. So if with this condition on eigenfunction, if the positive sequence satisfy again the same condition, then we have Hausdorff-Young Paley inequality. So in fact here also, if you put B is equal to P prime, then you get Paley inequality. If you put P is equal to P, you get Hausdorff-Young inequality, as similar to case in Rn. So is Now, after having Hausdorff-Young-Pele inequality, now our main result is LP-LQ boundedness of Fourier multipliers. So it's a exact analog of Hormander's theorem. So it says if you consider P between 1 and 2, and the Q is greater than or equal to 2 less than infinity, and assume that these two conditions are satisfied, then Fourier multiplier with symbol sigma, if it satisfies this condition, is given by on the right hand side. If this is finite, then A can be extended to from LP to LQ. So if this suppose the operator L is self-adjoint, then this is nothing but only it will appear V psi will appear, disappear, it will be U psi, and if it suppose it's just Laplacian on the torus, then it will be 1, and then you get a very fine condition in this case, but it's a very general. So now having Fourier multiplier, LP-LQ boundedness of Fourier multiplier, now we will discuss LP-LQ boundedness of pseudo-differential operators. So in this case, we need to assume little more. We need to assume that manifold M is compact manifold. So here, if eigenfunction satisfy again the same condition here, and then a pseudo-differential operator with symbol sigma A, if it satisfy this condition which says supremum over S greater than 0, Y is in manifold, and then symbol is regular, of course we have to assume smoothness in Y, and if it satisfy this condition for every beta less or equal to dimension of M over Q plus 1, where delta Y is a local partial derivative on the if it's in boundary. So this condition is only for when this has a non-empty boundary, and essentially if it has non-empty boundary, then we have to assume a little bit more that support of the symbol is contained inside the interior of the manifold. Okay, then with this condition on the symbol, A admit a bounded extension from LP to LQ. So these are the LP-LQ boundedness result in this setting. Now, when we have once we have LP-LQ boundedness, then these kind of result are applicable to study well-posedness or of partial differential of equations. So the first result is not very it's a standard application of boundedness result in PDE. So first we consider heat equation with here abstract heat equation. You can say we consider Fourier multiplier as given by a linear operator of Fourier multiplier in this setting. So this is a heat operator. In general, for heat operator we have here Laplacian. Here we consider a operator here in abstract Cauchy problem or abstract nonlinear heat equation. Then this equation, heat equation, is said to be had is admit a solution U if it satisfy condition 20 in the space, in this space. Now having this definition, and this actually this is a global solution, and we say a Cauchy problem, this Cauchy problem or nonlinear heat equation admit a local solution if there exists T naught such that this hold. So it is for every, and this is for the exist. So it's called local and this is called global. So now having this definition, we have two theorem about the existence of the solution here. Well, like between P and 2, suppose B is a Fourier multiplier. Now here it was a general operator if you consider as a Fourier multiplier, as in our theorem we discussed with those conditions. In fact, then the Cauchy problem Fourier multiplier from L2 to L2P, and now here 2P, P between 1 to 2, so it's a Q, and Q is now above than 2. Because Q was already from 2 to infinity, so these conditions satisfy here. Then the Cauchy problem, this problem here has a local solution in this space. And in fact, if you consider a general pseudo-differential operator or a general linear operator with the symbol this satisfying all the condition on that theorem which we discussed, LPLQ boundedness, then it also has a local solution. Now now we consider wave equation, nonlinear wave equation. So the wave equation is given by this. So the similar definition also work here. So we say that nonlinear wave equation has a global solution if it satisfies this condition 22 in the space L infinity 0 t L to m for every t, and if it hold for a specific for a particular t for some t, then it's called a local solution. So in this case we also have similar theorem. So first theorem is we need to assume if this is bounded, if B here this term is bounded by L2 norm, then the Cauchy problem has a local solution. And if U1 is identically 0, if U1 is identically 0 here, this U1 is identically 0, and gamma is greater than 3 by 2 with this and which is with this condition on bound with B, then we get a local solution, we get a global solution for Cauchy problem. So and this theorem use the idea of Banach fixed point theorem. So and Banach fixed point theorem idea are very standard in PDE. So now we consider a particular example of our model operator L. So the first, this was so this is called unharmonic oscillator. So unharmonic oscillator is a can be served as generalization of harmonic oscillator as without this one condition, because harmonic oscillator is given by minus times Laplacian plus mod x square, and this is a generalization you can thought of as a generalization. And this unharmonic oscillator is recently studied by Mariana Chadjaku and Delgado and Michael Ruzhansky. So this is a particular case of our operator L, because this has discrete eigenvalues, and this is a operator which, but here is a Rn manifold without boundary, so we don't care about boundary. So the same analysis work here in this setting. Now this operator is also a pseudo-differential operator because it arises using the Y quantization formula from the symbol. Now this unharmonic oscillator also arises as a global symbol, I should say, which was studied by Ruzhansky and Veronique Fischer in different settings. So like harmonic oscillator arises as a global symbol of sub-Laplacian on Heisenberg group, and this unharmonic oscillator arises as a global symbol of Engel groups and Cartan groups, which are step 3 and 4 groups. Now the exact problem of this unharmonic oscillator is still not known. In fact, for quartet case, when this is 2 is not exactly, is still is unknown, which is given in this reference in 6. But we know that the spectrum is discrete and the eigenfunction are, of course, is indexed by natural number. So here, having this detail, now in this case we also have explicit eigenvalue counting formula for this operator unharmonic oscillator, which was actually calculated using the more general setting of Topt and Bujano, Bugiotto and Rodino in the paper of Mariana Chadjaku and Delgado and Ruzhansky. So now in this setting, now this operator, actually this operator unharmonic oscillator is a self-adjoint operator, so you don't have to worry about the conjugate problem or anything. So with this is just Fourier multiplier we define like this, and then in this setting, that theorem which we discussed earlier about Fourier multiplier is just turns to be take this form. So here this we get L infinity norm of eigenfunctions, and it's very simple. Now we will study here using this theorem of LP-LQ boundedness. We will study the spectral multiplier of the anharmonic oscillator here. So now this is our kind of end result in the setting. So here, if this P and Q satisfy this condition, which was in the first theorem also, and if you consider phi, so we need for a spectral multiplier, for a spectral multiplier we need to we need to find the condition on the function P such that the operator phi of L is bounded from LP to LQ. So if you consider function P is a decreasing function from 1 to infinity, because the spectrum of this operator anharmonic oscillator is lie from 1 to infinity, such that phi of u vanishing at infinity, then the spectral multiplier of anharmonic oscillator is bounded by this quantity. So if p is such function such that its growth is not greater than inverse of this function, then it's bounded. So it's a very nice spectral multiplier theorem here, and the proof is very simple. So let us because I think we have time. Okay, the one we have time.
Yes, you have 6 minutes.
Okay. So I will explain quickly. So for the so in this case, now the symbol of this spectral multiplier is nothing but phi of lambda j is a sequence. So we apply the first theorem of Fourier multiplier, because spectral multiplier is also Fourier multiplier with symbol phi of lambda j. Then we apply this the first theorem which we prove in this setting for this Fourier multiplier. Then you get, instead of symbol, you have phi of lambda j here and this condition. Now after that, this is a technical inequality which we use here, that L infinity norm of eigenfunction is bounded by eigenvalues. And we use the fact that phi is less or equal to phi of 1 because it's decreasing, and for S here we get this inequality, this bound. Now it is only matter to calculate this fact. So this will follow you using the while eigenvalue counting formula which we have here. So because u goes to infinity, then you take u such that it is approximating to some eigenvalue lambda uj, and then you take u is square outside, and then you get while eigenvalue counting formula here. So it's just n of lambda j, which is while eigenvalue counting formula, and we have formula for this. What is that? Is just this one. Then approximately we get this and put it here, and then we get the main result. Now this spectral multiplier theorem actually gives very nice estimates for different like it gives heat kernel estimate and also Sobolev type estimate in this setting. So first one is a corollary of that because we can take phi of p is x power minus 1 and minus m, and then is give negative boundedness of negative power of anharmonic oscillator from LP to LQ. So in particular, negative power of anharmonic oscillator is bounded if the power is greater than this number. In particular, this is bounded from L2 to L2 for every m. Now, now if we choose phi is equal to 1 upon u power a minus b, then this function satisfy all these conditions which we have. It's a decreasing function. It's going to set infinity and everything. Now we apply that theorem and we get this inequality here. So here using this inequality, so here we need to this condition a minus b is greater than 2. Then with this condition, I think is then this is we get a estimate. So we apply this our spectral multiplier theorem here. This one for p is equal to 1 upon u upon a minus b, then this will be a minus b u is less or equal to this quantity. So here is a b minus a, then you transfer this a minus b here and you get this inequality which is Sobolev type embedding type for anharmonic oscillator. It's a version of in this case, for of course where a and b is greater or equal to this number. And then finally you consider heat equation, anharmonic heat equation, and this is the solution of this. And then you apply the same theorem with function phi taking exponential of tu, then you get heat asymptotic estimate of the heat solution of the heat equation. And thank you.
Okay, Vishvesh, thank you very much for your very nice presentation. Now we are open for questions. Any questions? Please use the system of virtual hands to do some questions. Okay, I have one question by myself, if I may. Vishvesh, I know you are expert in symmetric spaces. Then
I'm not expert, but I know a little bit.
do you know some kind of results for LP-LQ boundedness of differential operators or multipliers in the case of symmetric spaces?
Actually, for LP-LQ boundedness of pseudo-differential operator, even the study of pseudo-differential operator on symmetric spaces is very less. In fact, we study recently for compact symmetric spaces, you can say. But for LP-LQ boundedness especially, I would like to mention here paper of Colling, Mosseri, and Mehta. They study Fourier multiplier, but not exactly Fourier multiplier. They study heat equation or some special kind of Fourier multiplier. More than that is not known. LP boundedness is a very famous paper of Professor Ankers, which appear in Annals of Mathematics, but LP-LQ is not yet settled.
Okay, we have one question of Julio, Professor Julio.
Sure.
Hi, Vishvesh.
I'm fine, Julio. How are you?
Good. Thank you for your talk.
Thank you for having me.
Very interesting. So I have maybe two questions.
Yeah, sure.
So for the LP boundness of these negative powers of an harmonic oscillator.
Yes.
Can you go back?
Yes,
on
sure.
the slides?
Yes, yeah.
So I think maybe in some cases maybe they are compact.
Yes. I think we didn't actually consider that because actually Mariana started writing her thesis, and then
okay.
But we will actually discuss more about these things. Yeah.
On the other hand, I don't remember the number of the slide, but about the Horman-Dermilin extension that you.
Okay. Yeah, yes. I will go back.
LP.
Yes, sure. It's here.
But you have, for instance, that one, you have this condition on S.
Yes.
S greater than max. Is that condition sharp?
No. It's not sharp here. Even Duvan studied this for Hermite multiplier, Hermite pseudo multiplier. This condition, I don't know. In that case also is because it depends upon the sharp bound of the eigenfunction itself. So
okay.
So it's not sharp here, in fact, because it's a more general condition. If you study maybe for Hermite multiplier, maybe it's kind of we obtain sharp condition. But here is it's very general setup. So we don't know.
Okay, thank you. And
thank you very much.
And thank you for accepting to participate in this conference.
Yeah, thank you.
You are maybe the only non-Spanish
speaker. But it's
I guess
not my fault. Actually, the one who teach me Spanish, he was only teach me uno.
Thank you very much.
Okay, so I stop sharing now if we don't have any question.
No, then it's okay for me. Thank you. Maybe we can discuss later about some problem.
Of course, yeah. I was waiting for you to come here, but this corona ruined everything.
Okay. Thank
Okay,
you, Professor, for your questions. Thank you, Vishvesh.